Now that we've introduced the concept of recursion, it's important to understand how recursive calls can grow in complexity depending on the nature of the problem. In principle, a recursive function can increase the number of function calls exponentially if each call makes more than one new call, as in the case of the Fibonacci sequence. Let's look at the classic recursive Fibonacci function. The base case is simple. If n is less than or equal to 2, we just return 1. For n greater than 2, the function calls itself twice. Once with n minus 1, and once with n minus 2. Add those two values, and that's it. No loops, no arrays. Calculating Fibonacci for 7 is immediate. But for larger values, like 40, it becomes incredibly slow, because we end up recomputing the same values over and over again. The function values for 1 and 2 are given. Then, when calculating fib3, we call our function twice, for n equal to 2 and 1. Next, for fib4, we call it 4 times. For fib5, 8 times. For fib6, 14 times, and so on. By the time we reach fib40, the function is called more than 200 million times. In general, when a recursive function calls itself more than once, the number of calls grows exponentially. In such cases, we say that the algorithm has exponential time complexity. Our goal is to make it linear, resulting in the function being called only n times. This is where memoization comes in. It means storing the results of subproblems as we compute them. Let's use map to store the results. We can change the definition to have only integer values. First, we check if the value is already known. Be careful, as the key not found is an example of a reverse logic. Now, if this output is true, get the n value, calculate the function, and write the n and its value into map. We still need to create an input and output for this map and connect our recursive calls. Now, when the key is found, don't calculate the function, just read the value from the map. Basic case, simply pass those values through. With this technique, we reduce the time complexity from exponential to linear because we solve each subproblem only once, and the result is almost immediate. No loops and no arrays. You can use different options to store the data, like variant, or your own functional global variable. Now let's shift to another famous recursive problem, the Tower of Hanoi, which involves moving disks from the source peg to the target peg using a spare peg, ensuring that a smaller disk is always placed on top of a larger one. To achieve this, we first move the n-1 disks from the source peg to the spare peg. Then move the largest disk from the source peg to the target peg, which is our base case with no further recursive call. And finally, move those n-1 disks from the spare peg to the target peg. To solve this, we write a recursive function that includes instructions on what to do, along with the specified number of disks and the names of the pegs. Our base case, where no recursive call is made, is moving disk number 1, the largest one, from the source to the target. Then, if we have n disks, we move the nth disk from the source peg to the target peg. Before the recursive call, we update the disk number to n-1, assign the target peg to act as the spare, and the spare peg becomes the new target. Finally, we move the n-1 disks from the spare peg to the target peg, using the source peg as the spare. The Tower of Hanoi has a clear recursive structure, but it still demonstrates exponential growth. The number of steps doubles with each additional disk. With just a bit of effort, you can visualize these moves using the picture indicator.